Alright, so let's talk about advanced issues regarding the beam problems. So we are still talking about the beam problems. So up to the last time, we consider very simple problems of beam. So we consider only one material. So we consider only single material for your beam cross section. But in reality, so we have many different engineering applications where we use multiple materials. So for example, if you consider this building, so if you I wonder if you ever seen any the construction field. The construction field, you can see the steel reinforcement and also concrete. Yeah. So most of structural members consist of multiple material like concrete and steel reinforcement, even PSC tendons too. Okay. So in the case of non-structural members, so we have plastic and then the particulate board, like in this table, so in many cases. Okay. And then also the last week, I got a question from a student that what is the reason that we use the concept of shear flow instead of shear stress? Okay. So in the lecture note 5, in the lecture up to lecture note 5, actually we don't need the concept of shear flow actually. But here we want to discuss the deficiency of beam theory in this chapter. Okay. So make sure that in the case of beam theory, so we do not consider any three-dimensional position where we apply the load. So we only consider two-dimensional configuration. That's the beam theory. Okay. Two-dimensional configuration. So we never discussed where we apply the external load here. So depending on the position where we apply the external load, the external load would produce what non-zero torsional moment to the cross section, isn't it? So to discuss that problem, so we need the concept of the shear flow. Okay. All right. So now let's talk about the advanced issues. So here the first one is outline. So as I told you, the first we want to discuss the modified or the extended flexure formula. So where we have multiple materials. So although in the textbooks we consider only two different materials in the cross section, but our consideration can be extended to very general cases where we have many, not infinitely, okay, and actually, actual problems, and most three, like at most three, or two, typically. And then also we want to consider, the bending of doubly symmetric beams. So when we consider the inclined load, okay. So up to the last point, we consider only the horizontal neutral axis. Neutral axis is horizontal. So that in two-dimensional problem, if you look at the neutral axis in the transverse direction, the neutral axis position was equal to just a point, is it right? But if you consider a very general case, the multiple bending moment, the bending moment with respect to y-axis, not y-axis, bending moment with respect to y-axis and also z-axis, then we have two different bending moments, two different directions. In that case, the direction of neutral axis also changes. Then we have very general consideration. And then we want to also talk about how we analyze unsymmetric beam, okay, unsymmetric beam, and also we want to discuss the location of shear center cross section. Actually, in your textbook, why we discuss what's the nature of the shear center clearly, but here I added more information to help you understand the concept of shear center and why the shear flow is useful to evaluate the shear center. Okay. So key point before we move to the the place for the shear center, the key point is that everything comes from the deficiency of the beam theory. The beam theory is not complete. Okay. Actually, this is a kind of simplification. So we describe everything in two-dimensional space. Okay. That's why we have such a deficiency. So if you want to design by structure using the beam theory, then I don't want to have any situation so where my beam deficiency is found. Okay, that's the key point. Is it clear? Okay. So if I explain you again in 우리말, 빔 이론 자체가 불완전한 거예요. 빔 이론 자체는 그 2차원 평면에서만 작용되는 거예요. 그래서 하중이 2차원 평면 말고 이쪽으로 어디 작용하는 건 절대 얘기하지 않아요. 그러면은 하중 작용하는 여기 있거나 여기 있거나 여기 있거나 밴딩 모멘트는 다 똑같이 나와요. 빔 문제에서는. 그런 거잖아요. 2차원이니까. 근데 만약에 하중이 여기 있으면은 당연히 비틀림 모멘트 만들 거잖아요. 그치? 그래서 이 얘기 하는 거예요. 그러니까 빔 이론으로 했을 때 시어 플로우가 비틀림 모멘트를 만드는데 그 비틀림 모멘트하고 똑같은 비틀림 모멘트를 발생시키는 포지션을 찾는 거예요. 그래야지 서로 캔슬이 되는 거니까. 근데 만약에 이제 빔 티어리를 이용 안 하려면 괜찮아요. 그러면 풀면 다 나와요. 근데 빔 티어리를 지금 사용하고 싶은 거 그래서 그런 거예요. Okay, let's revisit the issue. Okay, when we discuss the shear center. Okay, and then also this distribution of shear stress here. And then I'd like to give you a little bit, some very shallow information regarding the elastoplastic beams. Okay, the first one is the composite beams. So here we have some of examples of composite beams. Okay, the composite beams are fabricated of more than one material. For example, the first one is bimetal plate. To measure, we use this bimetal as automatic switch. If you heat up, and so it turns off automatically because of deformation. Okay, and then this is a tube, the plastic coated tube, and also, as I told you, reinforced concrete beams. So where we have so if you consider reinforced concrete cross section, typically it is full of steel reinforcement, isn't it, right? This is steel reinforcement. So we have steel and concrete, okay? So we use two different materials for the reinforced concrete beam. And then now in these days, because of the carbon, okay, the carbon issues, now many people are interested in the use of wood structures, okay? So now the wood structure alone, actually it is not enough to reduce the structural load, isn't it? So in that case, we want to reinforce the wood cross section by using steel plate. So here we use two different materials, okay? So let's talk about the problem one by one. So don't be surprised, because we have, more than one materials, okay? The key point is always same. So the analysis procedure is always same. First, we have to, define the deformation, okay? Once we have deformation, using the compatibility condition, we calculate the strain field, okay? Strain field. Then if we have a strain field, the next step, we calculate the stress. And then if you have stress, we calculate the internal forces. And then we check, force equilibrium with the external forces. And then that's, the same procedure is applied to even to this problem. Okay? No difference, okay? So now let's talk about the definition of deformation first. So how do you define the definition of deformation of beam problem? As I told you, if the beam is small deformation beam, so we want to use what? We want to use the curvature, okay? The curvature to measure the deformation of beam. The curvature is approximated further by the second derivative of deflection for the small deformation beam, okay? So we still want to use the curvature, okay? We still want to use the curvature to define the deformation. And then if my beam is small deflection beam, this curvature is approximated as second derivative of the deflection. Okay, still same. So make sure that the kinematics is independent of equilibrium. Okay, kinematics is independent of equilibrium. I told you several times. Okay, the connection is what? Connection between the kinematics and equilibrium is, what is this? Constitutive law, material law. So using the material law, we can connect these two. Otherwise, they are independent of each other. Okay, that's why. So there's no problem. So we consider kinematics without thinking the equilibrium. Okay, forget about equilibrium. So first, I want to consider the kinematics. So to describe the deformation, I want to use the curvature. And then its approximation is second derivative of deflection. Okay? The further, I want to introduce another simplification to describe the deformation of beam. Here, the displacement compatibility. What I mean, my strain is linearly distributed in the cross section. Okay, linearly distributed cross section. So here, my strain field, the strain value at a position depends on the coordinate, the curvature, and then we want to multiply the y coordinate. Okay, isn't it? Yeah. So please make sure this. So we have displacement. Okay, displacement. We have displacement, and then I calculate the strain. Okay, so I'm doing exactly the same job. Okay? And then what? I calculate the stress, and then I calculate the corresponding forces. I do the same. Okay, so in this problem, I will use the curvature to describe the deformation, and then I just calculate the strain field. My strain field is equal to minus curvature and y coordinate. Okay? Isn't it, right? And then what is the next step? The next step is I want to calculate the stress value. Look, for this cross section, my strain distribution is linear. For example, like this, linear, okay, linear. Doesn't matter, we have 3 materials, 4 materials in this cross section, okay, doesn't matter, linear. And then I need to multiply the elastic modulus. So we have elastic modulus for wood and elastic modulus for steel here, isn't it right? So obviously the elastic modulus of steel is much greater than the elastic modulus of wood, isn't it? That's why if you do that, my stress field would look like this. The elastic modulus of wood is smaller than the steel. That's why this is my stress distribution. But at the interface between the wood and steel, my stress increases significantly. Okay? Let's say the elastic modulus, at the same point, my strain is, say, for example, 0.01. But my elastic modulus of wood is, for example, 1000. Then 1000 times 0.01 is equal to 1, isn't it? But if you multiply the elastic modulus of steel, let's say 10,000. If you do that, my stress becomes 10, okay? So distribution of stress must have discontinuity, okay? It's not continuous. But in the case of strain distribution, it's continuous according to my displacement compatibility, according to the definition of my displacement field. Clear? Okay? So that's why here I put an index here, subscript. So my stress of ith material, can be calculated by multiplying the elastic modulus for that material, the ith material, to the strain value. Okay, to the strain value. So we have strain here. My strain is minus times minus curvature and the y coordinate. Okay? So where are we? Now we are here. My stress, if I have ith material, this is equal to elastic modulus times strain. Okay? Isn't it right? So what's the next step? So now we are talking about the beam problem. Next step is we need to collect all the contributions to the internal bending moment. That's what you have to do, isn't it, right? That's what. Next step is here. Next step, probably we need to calculate the moment contribution, the small moment. The small moment is what? Small moment is, and then small force times the distance, arm length, isn't it? And here small force is equal to the stress and the small area. Okay? So if you plug in here, everything is straightforward. So Y and sigma dA. Okay. And here the stress is what? Sigma is elastic modulus curvature times Y. So let's plug in here, then minus elastic modulus curvature Y square in dA. Okay? So now I have multiple materials. For example, so look at this. My integration is for the area, the position. So if I have multiple materials, then let's say material 1, then we need to consider the elastic modulus for material 1. The curvature is the same, isn't it, right? And then Y square in dA plus the minus elastic modulus of 2, the curvature Y square dA. This is exactly the same as before, okay, except we have different materials. Do you have any questions? Is it okay? Okay. All right. This is what I told you. So although the strain, if you have two different materials, the strain is smooth. Okay. So across the interface, the strain is smooth because this is our assumption regarding the kinematics, the deformation. The distribution of strain is linear. This is my assumption. And then we multiply elastic modulus to the strain field. Elastic modulus 1, the elastic modulus 2. Because these two values are different from each other, this is inevitable to have discontinuity at the interface of two materials. Clear? Now let's talk about the position of neutral axis. So because this is beam problem, the sum of all the force, the normal direction, should be equal to 0, isn't it, right? Then some small forces becomes what? The integration of stress of individual materials over its own area, okay? Over its own area. In this problem, so we need to integrate normal stress for material 1 and then for material 2. It should be equal to 0. Okay? And then I want to plug the information of stress. Where is the stress? Here, stress. So I want to plug in here. So if you do that, this is for material 1, I have this, and for material 2, I have another equation. So make sure that curvature is a reference, representative information for a cross section. That's why we can cancel. Okay, we can cancel, isn't it? At any point in x coordinate, the curvature is the same because we want to calculate the curvature with respect to neutral axis. That's why this curvature is same as this curvature. Cancel. Okay. So the position of neutral axis can be calculated by using this equation. Okay. So let's do an example for the calculation of neutral axis. Okay, let's consider a rectangular section. Here I have two different materials, material 1 and material 2. So obviously the material 1 is characterized by E1 and this is characterized by E2. And then this width is given by B, and then the first part, so let's say for example H1, okay, H1, and the second part H2. Okay, this is a simple description. Okay, so key point is this: the first moment is equal to 0. Okay, so E1, and then for Y1, YDA plus E2, YDA is equal to 0. So if you have any, if you know the position of neutral axis here, if this is Y, the problem is we don't know the position of neutral axis. Isn't it right? That's the problem. I don't know that. That's why I want to introduce the coordinate Y prime. So I already know the reference point. So I want to consider this bottom surface, okay, Y prime. And then distance to the neutral axis position. So I want to call this as Y bar. So I'm doing exactly the same job that I did before. That's why, my Y plus, so Y bar is equal to Y prime. Okay? Does it make sense? What do you think? Yeah, it makes sense, right? So that's why the Y, the coordinate measured from the neutral axis, is equal to the reference coordinate. Okay, the reference coordinate that we fix to the bottom surface minus the distance to the neutral axis. So now let's plug in here. So if you do that, E1 Y prime minus Y bar PA plus E2 Y prime minus Y bar PA is equal to 0. So here, then E1 Y prime dA first moment, E2 1 2 dA is equal to the distance Y bar, isn't it right? Y bar, and the E1 times A1 plus E2 times A2. Is it clear? Isn't it right? Okay, that's why position of neutral axis can be calculated by using this formula: E1 A1 plus E2 A2, and then the first moment. So E1 of first moment, this is what? First moment to this is what? A1 times the distance to the geometrical centroid is what? H1 divided by 2, isn't it? H1 divided by 2. And then E2, and the cross-sectional area of material 2. And then I'm talking about this. The distance to the geometrical centroid is what? H1 plus H2 divided by 2. Okay? It's very easy, right? That's how we can calculate the position of the neutral axis. Do you have any questions? 질문 있어요? So if you divide, for example, E1 from the numerator and denominator, this is very instructive. So if you do that, let's divide this, cancel, and then we have E2 divided by E1. E2, E1. The ratio of elastic modulus, sometimes instead of using the elastic moduli as is, okay? But instead of that, we use this modular ratio. This E2 divided by E1 is called modular ratio. Modular ratio. Modular ratio. Okay, so here today, let me start my lecture here. So, 지금 강의시간 많아? 좋은 거 많지. So let me start my lecture here. See you next time.